Okay, so today we are starting our probability unit. We are going to start with some vocabulary. Okay, the first one is, what is an experiment? An experiment is an action or trial with varying results. What's an example of an experiment? What's an example, though, of it? Rolling a dice, thank you. Okay, next is an outcome. An outcome is a possible result from the experiment. So if I'm rolling a dice, what's a possible outcome?
1.
I heard 1 first. We'll go with 1. That's a possible outcome. Last vocabulary word, sample space. What's the sample space? It's the set of all possible outcomes. So, again, if we're talking about rolling a dice, use your set symbol, which is that curly bracket. What are all my possible outcomes of rolling a dice? 1, 2, 3, 4, 5, and 6. Close your curly bracket or your set. Good? Okay, so we are going to draw some tree diagrams. Okay, tree diagram is a very useful way of finding the sample space when there are multiple actions. Draw a tree diagram, then list the sample space and determine the number of outcomes for each scenario. So, picking a digit 1 through 8. So, if I'm picking a digit 1 through 8, I can pick 1. I could pick 2. I could pick 3, 4, 5, 6, 7, or 8. Those are my different possibilities. Okay. Now, if I pick 1, then tossing a coin. What are my options for tossing a coin? Heads or tails. So if I pick 1, it's either going to be heads or tails when I flip my coin. If I pick 2, I'm going to have a heads or a tails when I flip my coin. So all of these numbers I'm picking, I then am flipping my coin, and I have 2 possible outcomes when picking the coin. Do we see why this is called a tree diagram? Does it look like these are branches or roots? Good? So then we are going to do our sample space. Remember sample space, do your curly bracket. Do what? Yes, 1H and 1T. 1T. Or 2H or 2T. 3H, 3T. 4H, 4T. 5H, 5T, 6H, 6T, 7H, 7T, 8H, 8T. So let's count up our possible outcomes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 different ways this could happen. 16 possible outcomes. Good? Are you okay with that? Okay. Randomly guessing the answers to the last 3 questions, multiple choice questions of a test if there are 4 options for each question. So, question 1, question 2, question 3. Okay, question 1 has how many possible choices? A, B, C, D. So A, B, C, D. A, B, C, D. A, B, C, and D. So now let's do our sample space. Question 1 can be A, question 1 could be B, question 1 could be C, question 1 could be D. Question 2 could be A, question 2 could be B, question 2 could be C, question 2 could be D. 3A, 3B, 3C, or 3D. Those are all the possible outcomes. And then count up how many there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different outcomes. Good? Are we okay with doing our tree? We're doing one more. Okay? Choosing a day a week and then choosing a letter from the word math. Do we actually want to write out all the days of the week, or can we just do like 1, 2, 3, 4, 5, 6, 7? Because there's 7 days, right?
Yeah.
Okay. So, day 1, day 2, day 3, day 4, day 5, day 6, and day 7. So I'm choosing one of the days of the week. Then I'm choosing a letter from the word math. So M, A, T, H for all of my days. Make sure you are doing this, guys. You are having a quiz over this. Could you potentially have a quiz question that's asking you to draw the tree diagram? Yes. So actually practice drawing the tree diagram. Does it seem kind of tedious? Yes. Extremely. I agree. But do you have to do it? Yes. So we're going to list out all the different options. 1M, 1A, 1T, 1H. 2M, 2A, 2T, 2H. 3M, 3A, 3T, 3H. 4M, 4A, 4T, 4H. 5M, 5A, 5T, 5H. 6M, 6A, 6T, and 6H. 7M, 7A, 7T, 7H. So there's my sample space. What are my possible number of outcomes? 28. Is anyone catching on to a pattern?
Yeah.
What's our pattern?
Multiply.
You multiply the number of outcomes for the first experiment, and then the number of outcomes for the second, and when you put them together, that's the total number of outcomes. 7 days of the week times 4 letters in math give you 7 times 4, which is 28. Same over here. 1 through 8 is 8 options, and then tossing a coin is 2 options. So 8 times 2 is 16. 3 questions, each with 4 options. 3 times 4 is 12. Okay? So that is the fundamental counting principle. You can use the counting principle to find the total number of outcomes. If one activity can occur in M ways, and another activity can occur in N ways, then both activities can occur in an M times N number of ways. So you just multiply the two number of outcomes. Okay? So let's do these instead of doing the tree diagram. Choosing a month of the year. How many months are there in a year?
12.
So that's 12 times a digit 1 to 9, which is 9. 12 times 9 is... Do you see why you would want to use the fundamental counting principle instead of doing a tree diagram for this? I don't want to do 108 different possibilities. Okay, choosing a letter of the alphabet. How many letters are in the alphabet?
26.
Times tossing a coin. 2 options, so 26 times 2 is... Choosing a pair of pants, a shirt, a belt from 3 pairs of pants times 5 shirts times 2 belts. So can it work with 3 things? Yes, you're just multiplying now by the probability, or sorry, the number of options there are for the third piece. So 3 times 2 times 5, 30 options, 30 combinations. Rolling a standard die 4 times.
24.
Mm.
6.
Mm.
6 times 2.
Okay, so you're rolling a standard dice once. How many options are there?
6.
Times rolling a standard die again. Rolling a standard die again. Rolling a standard die again. So it's not 6 times 4 because there's 6 options 4 times, so 6 to the 4th power. Or 6 times 6 times 6 times 6. 1,296. Okay. Choosing one student from a class of 32 students times choosing a student from another class that has 27 students gives you 864 different options or combinations. Spinning the spinner to the left. How many options are there on the spinner to the left? 16. How many times are you doing that? 3 times, so you can do 16 times 16 times 16, this spinner over here. Or you can do 16 to the third, which is what?
4,096.
4,096. Tossing a coin 5 times. How many options are there when you toss a coin?
2.
2. And you're doing it how many times?
5. Power 32.
Which is 32. Again, could you write that out as 2 times 2 times 2 times 2 times 2? That's the same as 2 to the 5th power. Okay, creating a 4-digit password from 0 to 9.
4 to the 9th power.
How many options are there for digit 1?
9. 10.
10.
0.
0. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so there's 10 options for the first digit. How many options are there for the second digit? 10, the third digit. The fourth digit. 10. So it's just 10 to the fourth power, which is what? 10,000. Do you see how a 4-digit password can be super hard to crack? There's 10,000 different combinations. Do what?
I have a 60-digit password.
Yeah, that's why passwords are difficult to crack.
Well, yes, but usually passwords are connected to multiple personal lives, so they're not really up to chance unless you decide to random password.
That's why it's a good idea to change your password regularly.
Yes.
And to not use the same password for everything. Although I do.
I just changed my.
That's why if somebody finds my password out, can get into my house, my car, my neighborhood, my bank, my...
Probably should have been done.
Good luck finding my 4-digit password. There's 10,000 options.
Guys, if you split the work, it won't be as hard.
Yeah. Divvy it up. Pretty sure you'll get locked out of stuff, though, before you get the right one. Okay. Last one of these guys. Choosing a perfect square number that is less than 50. Oh, we need to know some vocabulary. Perfect squares. What I would do is start with 1. 1 squared is what?
1,
2 squared.
4,
3 squared. 4 squared. 5 squared. 6 squared. 7 squared. 8 squared. But that's not less than 50. So that's 1, 2, 3, 4, 5, 6, 7 options. Times, how many letters are there? 9 letters. Give you how many possibilities? Good? Okay, now let's go to the next page, and we are doing theoretical probability. Probability is a measure of the chance that a specific event will occur. When all outcomes are equally likely, the theoretical probability of the event E is the ratio of the number of favorable outcomes to the total number of outcomes. So you just divide the number of times you would expect it to happen over how many total outcomes there are. We just did finding the total number of outcomes. Okay? Probabilities have values between 0 and 1. And they can be expressed as a fraction, decimal, or a percent. Okay? So, let's do the theoretical probability here. So, let's see. What is the probability of spinning a multiple of 3? So, let's think. What are multiples of 3? 3, 6, 9, 12, and 15. 1, 2, 3, 4, 5. So, 5 over, what's the total number of options when you spin?
16.
Does 5 over 16 simplify? No. So that's it as a fraction. Tell me it as a decimal.
3.3.
No.
0.31.
3125. And then let's do that as a percentage. How do you change a decimal to a percentage? So that would be 31.25%. Okay. Now let's look at the probability of a prime number. What's the only even prime? 2. So we don't have to check any of our even numbers other than 2. 1's prime, 2's prime, is 3 prime? We don't have to check 4 because 4 is even. Is 5 prime?
How do you know if it's prime?
Yes.
If it's prime numbers are divisible by only 1 in itself. So that's why no even numbers other than 2 are prime, because all even numbers are divisible by 2. Okay, 5 is only divisible by 1 and 5. What about 7?
1 and 7.
Only 1 and 7. What about 9? No, 9 is not prime. What about 11? 11 is prime. What about 13? What about 15? No. So we have 1, 2, 3, 4, 5, 6, 7 prime numbers. Over what's the total number of possibilities? Does that simplify as a fraction? What's the decimal? 43.75%. Okay. Now let's do an even number greater than 5. So an even number greater than 5. So is 6 even? What about 8? We're doing all even numbers greater than 5. So 6, 8, 10, 12, 14, 16. 1, 2, 3, 4, 5, 6. That's 6 numbers that are even greater than 5. Over 16 possibilities. 6 over 16 does simplify into 3 over 8. What is it? 0.375. 37.5%. Okay? And then an odd number at most, 9. Okay, so we're looking for odd numbers, but the most could be 9. So starting with 1, is 1 odd? Is 2 odd? No. 3 odd? 4? 5? 6? 7? 9? Can I include 9? Yeah, it says at most 9, so we can include 9, we just can't go higher than 9. So that's 1, 2, 3, 4, 5 possibilities. Over 16, which is the same as the probability of getting a multiple of 3. Good? Now, does that mean that you're going to, out of every 16 rolls, you're definitely going to have, or spins, 5 that are going to be multiple of 3s?
No, this is a probable.
This is just theoretical. This is what you would expect because all of the pieces on this spinner have the same area. Okay? So that's just what you would expect to happen. The more times you do something, the more accurate your probability is going to be. Okay? If you just flip a coin like 3 times, do you think there's a chance you could get just 3 heads in a row? Yeah, definitely. Okay? But if you do it like 5,000 times, do you think all 5,000 are going to be heads? No, it's probably going to be pretty close to a 50-50. I forget which one it is, but one of them's more likely actually than the other because one side of the coin's heavier than the other. So it's more likely that it's going to be tails because heads is heavy. The heavy side goes down. Good? Okay. Number 2. This says, give the answer to the following questions as a fraction in simplest form. So on your quiz, guys, if you tell me a fraction and it's not in simplest form, are you going to get 100% correct? Nope. It needs to be in simplest form. Okay, a pencil box contains 5 red, 12 blue, 10 green, and 3 yellow markers. If a marker is chosen at random, what is the probability that it is not yellow? So let's first figure out what's the total number of markers. 5 plus 12 plus 10 plus 3 is 30 total markers. Okay. Then we are doing, what's the probability of not a yellow? So how many of them aren't yellow? 27 of them aren't yellow. So if I simplify that, 9 over 10. No, this just says in simplest fraction form. Good? Okay. I will tell you last period, or on Friday, kids were like, how am I supposed to know the answer to this? So you have to, when we're doing probability questions, I'm expecting that you know certain things like how many sides are on a dice, how many cards are in a deck of cards. Okay? So, what is the probability of drawing an ace or a diamond from a standard deck of cards? So, how many cards are in a deck? 52. So that's my total possible number of outcomes. Now, let's do the probability of a diamond first. How many diamonds are in a deck of cards? How many suits are there? 4. 52 divided by 4 is 13. There's only 13 of each suit, guys.
Well, this is unfair, because what if I don't know that information?
This is stuff you're expected to know.
Yeah, what if I don't know?
Then you're probably going to get this one wrong.
Well, that's just unfair.
Well, have you ever played cards before?
On the
What if I
quiz,
ask?
can we
Have you ever
ask-
played cards before?
No.
On the quiz.
You're a
can we-
liar.
So.
So,
On the quiz, can we ask you like how many?
no.
What? Well, what if, I've played cards, but what if I don't know how many specific cards and suits? there are?
Well, you should be able to know.
That's a stupid answer. That doesn't make sense.
How many stupid questions do I get from y'all?
A lot.
Yes, but it feels like.
And they're gonna keep coming.
None, because there's no such thing as a stupid
You know
question.
how many cards, or a deck of cards.
See, what if I just
Okay,
know that it's
so-
You know whether or not you know how
Let's
many
think,
cards.
guys. There's 13 diamonds in, are we talking about diamonds? Yes, there's 13 diamonds in your deck. Okay? But then we also need to include drawing an ace. Okay? How many aces are there?
4.
4, but one of them's a diamond, right?
So you have to have 3, which means 16 over.
So 13 diamonds, and then there's 3 other aces that aren't diamonds. So there's 16 total for your ace and your diamonds. Simplify that, and we get 4 over 13. Good? Okay, number 4. Finn guessed on the last 3 questions, true or false questions, on his math quiz. What is the probability he got exactly 2 questions correct? Okay, so first of all, let's figure out what are the possible number of outcomes.
2.
So let's think.
6.
How many options are there for question 1?
2.
2. How many options for question 2?
2.
It's 2 over 3.
How many options for question 3? 2 times 2 times 2 is
8.
8. So it's going to be something over 8. There's 8 possible outcomes. So now we need to figure out what is the probability that he got exactly 2 correct.
4.
So let's draw this out. Let's say he got the first 2 correct and the last one incorrect. Let's say he got the first one incorrect and the last 2 correct. What if he got the first and the last correct and the middle incorrect? Are there any other possibilities where he could get exactly 2 correct?
No.
No, so that's 3. 3 options. Does 3 over 8 simplify?
No.
No, done. Good? Okay, 2 standard dice are rolled. What is the probability that the sum of the dots on the dice is at most 5? So let's first think, what is the total number of outcomes possible? But you're doing it twice. So 6 on the first roll, and how many options on the second roll? 6. So 6 times 6 is 36. So it's something over 36. Okay. Now let's think. We're going to write these out. Okay. So if I roll a 1 and a 1, would that work? Is that At most 5?
Yes.
Yeah, that's 2. Okay, what if I rolled a 1 and then a 2?
Yes.
Yes, that's 3. What if I rolled a 1 and then a 3?
Yes.
That's 4. What if I rolled a 1 and a 4?
Yes.
That's a 5. What if I rolled a 1 and a 5?
No.
No, that doesn't work. Okay, so we're done with rolling our 1s first. What if I roll a 2 and then a 1?
Yes.
What if I roll a 2 and then a 2?
Yes. So you can't do 2.
What if I do a 2 and then a 3?
Yes. No.
Guys, it says at most 5. If it's at most 5, can it include 5?
Yes.
Yes, just not more than 5. So can I do 2 and 4?
No.
No. So let's go on to rolling a 3 first. 3 and what? 1. 3 and?
2.
3 and 3?
No.
No. Let's go on to 4. 4 and?
1.
4 and 2?
No.
No, because that'd be 6. Can I roll a 5 on my first dice to fit this situation?
No.
No, because the second dice I would have to roll the smallest number's 1, so 5 plus 1 is 6. That's more than the at most 5. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 options.
3 over 12.
Do what?
1 over 12.
5 over 18. So, we don't have to do our tree diagram to find all of our different possibilities, but do we potentially need to write stuff out to figure out the outcomes that will work? Yes. Okay. Now we are going to go on to Venn diagrams.
Is this the last one?
Yep. Okay, students in a homeroom were asked if they have a part-time job and if they have their driver's license. The results are shown in the Venn diagram to the left. If a student from the homeroom is chosen at random, find each probability, give each answer as a fraction in simplest form. So let's first look at the Venn diagram and figure out how many total students do we have, guys? 25, because you're just adding up all of the different possibilities. So there's 25 total. So whenever I do my part-time job, I'm going to look at students that are in the part-time circle. How many students are in the part-time circle? 14. There's 8 here and there's 6 there. Those 6 are in the part-time circle. So how many total are in the part-time circle? 14. It's just those 6 are overlapping also in the driver's license circle. Does 14 over 25 simplify? Nope. Okay. Yes, always simplest form. What's the probability that you don't have a driver's license? No driver's license.
12.
So I'm going to add up the ones that aren't in the driver's license circle. Okay, so that's 4 and 8 for 12. Over how many total students? 25. Does 12 over 25 simplify? Nope. Okay, what's the probability that you have a part-time job and a driver's license? That's just 6, because you're looking for the overlap. 6 over 25. What's the probability that you have a part-time job or a driver's license?
21 over 25.
So this time we are adding up any that are in the part-time or the driver's license bubble. So 8 plus 6 is 14 plus 7 is 21. 21 over 25 does not simplify. And then what's the probability that you have a driver's license and no part-time job?
7 over 2.
So that's just looking at the one that's just in the driver's license bowl. So that would be 7 over 25. That you have a driver's license but no part-time job. So we are going to look at the driver's license circle, but we can't include the 6 because those 6 have part-time jobs. Good? Okay. Next one. Out of 60 students, 15 are taking calculus, 27 are taking physics, 8 of the students are taking both calculus and physics, If a student of this group is chosen at random, find each probability. So let's make our own Venn diagram for this. So this is going to be my cal. This is going to be my physics. Okay. So it says that there are 15 students taking calculus, 27 taking physics. So can I put 15 in the calculus circle? No, I need to start with how many are taking both.
No,
8 are taking both. So the 8's going to be in the middle. So then you have to subtract. So if 8 are taking both and only 15 are taking calculus, how many are taking only calculus? 7. If 27 are taking physics, but 8 are taking both, how many are taking just physics? 19. Okay. How many students are taking neither? How'd you get 18? But it's 60 minus 7 minus 8 minus 19. 26. Okay, so what's the probability that a student takes calculus or physics? So that's looking at the calculus and the physics bubbles. 34. Over how many total students were there? Simplify that. Do what?
17 over 30.
17 over 30. So what's the probability that a student takes calculus but not physics? So we're just looking at the calculus bubble. So 7 over 60. Does that simplify? Do what? No, that does not simplify. Good? Okay, next we are going on to the complement of an event. What is the complement of an event? The complement of an event is the probability of the event not occurring. Since the sum of all probabilities in a sample space is 1, the probability of an event not occurring is 1 minus the probability that the event will occur. That little tilde E means not E. Okay, what's the probability of not E happening? So, number 8 says the probability that it will rain is 11 over 15. What is the probability it will not rain? So then you just do 1 minus 11 over 15, which is what? So, which is just 4 out of 15.
You're confusing me with that.
I'm just using this formula.
I feel like doing it off your head is easier.
Do what?
But I feel like doing it off your head is just easier.
Okay. A number from 1 to 30 is selected at random. What is the probability of not selecting a multiple of 4? So let's first find the probability of a multiple of 4. So let's think. Multiples of 4 less than 30. 4, 8, 12, 16, 20, 24, 28. So that's how many? 7. So 7 out of 30. So to find the probability of not selecting a multiple is I would do 1 minus 7 over 30, which is 23 over 30. Okay? Good? Okay, now we are going to go to experimental probability. We've been doing theoretical, what you would expect to happen. Okay? Now we're actually going to look when somebody did these experiments. First, we're just going to fill out the probability of the theoretical, and then we'll do the experimental. There's 1, 2, 3, 4, 5 possible outcomes, colors. Okay? So what's the probability of spinning an orange? How many oranges are on here? Not here. How many oranges are here? 1. Out of how many possibilities? 5. We are just doing the theoretical. We're not looking at the actual experimental yet. What's the probability of getting a red or a green? 2 out of 5. And what's the probability of getting not purple? 4 out of 5. Okay, so those are all the theoretical. That's what we would expect to happen. Then somebody actually spun the spinner 50 times, and this is the data they got. Okay? So, they spun 50 times, so I know my denominator is going to be 50. Okay? How many orange did they get? 12 orange. So, 12 over 50. Simplifies to 6 over 25. Okay, then the probability of red and green. 15 over 50. Which simplifies to 3 over 10. Okay, then the probability of not a purple. So that's add all of them up except for the purple. 43 over 50. 43 is prime, so that does not simplify. Okay, so let's see if 1/5 and 6 over 25 are very close to each other. So 1/5 and 6 over 25. Are those pretty close?
Yeah.
Yeah. Okay. 2/5 and 3 over 10. Are those pretty close? I mean, ish. Okay. And then 4/5 and 43 over 50. Are those relatively close? Yes. Now, if they did this 500 times instead of just 50 times, do you think that the experimental probability would get closer or further from the theoretical? Closer. The more times you do the experimental, the closer it's going to get to your theoretical probability. Okay? We good? Okay, so that's the end of our first day.
Perfect.